So, good afternoon, everyone. So, today I'll be presenting an overview of temporal logic and formal verification of time series AI. And the motivation behind this topic comes from the growing need to make AI systems more accurate and also trustworthy and verifiable. So, let us quickly start with the agenda. So, we'll start from the foundations of the formal verification, temporal logic for modern developments, sorry, such as temporal logic, robustness semantics or robustness computation, runtime monitoring, and applications in trustworthy AI. So, why do we need verification? So, most machine learning ML systems are evaluated like using statistical matrices, which we usually know like accuracy, F1 score, right? But these metrics are useful, but they do not guarantee any safety aspect. For example, like let us take an example of anomaly detector. So it may achieve like 99% accuracy, but it may still fail in the real world scenario or in some critical event. And similarly, we see the autonomous driving, right? It may perform well in testing, but not in the safety constraint in the rare situation. So, this distinction is important because testing demonstrates correctness on the observed examples, but verification attempts to verify it on the critical scenarios. So, our stronger question becomes instead of like simply asking whether the model will perform good or not or highly accurate, we ask like can we mathematically guarantee that a system behaves according to some requirements, and this question motivates us the formal verification idea. So let us start with the formal verification itself. So, what it is? So, it is a process of mathematically proving whether a system satisfies a set of desired rules or specifications. So, main notation is simple notation will be like M models phi, as you can see in this screen. So, where M represents a system model, phi represents a specification. And in other words, we can say like we want to determine like whether every execution of system satisfies the desired property or not. So the typical workflow goes like this. So we'll start from the system, real world system. We have four steps. First is we model the system mathematically. Then we specify or define a formal specification. Then we apply the verification procedure. And finally, we determine like whether this property is holding or not, it is satisfying or not. So under unlike the testing, the verification, formal verification provides a mathematical guarantee rather than just empirical evidences. So now, what kind of properties do we verify? So, in the verification problem, we basically categorize it into two categories. So, the first is safety, and the second is liveness. So safety property, as its name suggests, it's like something bad never happens, and it's very important in the critical scenarios. So for example, like G not of crash. So here G and the not, these are like symbols we'll discuss more in depth in the coming slides, which we use in temporal logics. So it means like crash should never occur. So the important aspect of safety properties is that violation can be detected in the finite times and we keep on detecting it, right? On the other hand, we have liveness, which is a property and it states that something good eventually happens. And F is the term which we use for eventually. So G of request gives or tends to F of response. So it means that every request should eventually receive a response. So unlike the safety properties, liveness violations may require observing the system indefinitely before concluding that the property is violated. And these two concepts form the foundation of many temporal specification which we do have. So now let us understand like why temporal logic with simple examples. So many real world requirements involve time, right? Considering an example of water tank. So if a pump is activated, the flow rate should become high within 5 seconds, right? 5 seconds is just an estimation. So, this requirement cannot be expressed naturally using classical propositional logic because it involves the ordering, the timing, right? And the temporal logic extends this classical logic with operators that reasons about the events over the time. And it provides a formal language for specifying this dynamic behavior, like how much and if it's turned on, it should be increased or decreased for how much time period it should be. So it's kind of a automated verification and it makes temporal logic really useful for cyber physical systems, healthcare monitoring, etc. And like for example, here there is a graph and there is like a simple logic rule where we see like if pump is turned on eventually, so here 0 to 5 is the timestamp and the flow should be greater than equal to 10. So we can see before the timestamp of 5 there is an increment like above the 10. So this is just a simple real world example for understanding it. Now, temporal logics. So let us understand what it is. So, it extends the classical logic by introducing operators that describe how properties evolve over the time. Now, instead of asking like whether a system is true, we ask whether it is true now, later, always, or until another event occurs. So these now, later, always, untils, these are some symbols which we will discuss in the next slide. So a system execution is represented as a state of states, like sigma is equal to S naught, S1, S2. A temporal formula is evaluated over this sequence. And now the key advantage is that temporal logic allows us to formally specify the requirements that involves sequences, ordering, persistence, etc. So this capability makes temporal logic the foundation of the modern verification techniques. Now, logic operators. So there are four fundamental temporal operators. The first one is X, meaning the next. So it shows that the phi must hold in the next state. The second is F, which means like eventually. So F phi means that phi becomes true at some point in future, eventually at any time instant. So the graph is also showing the similar pattern. Now the third operator is G, which means globally or always. So G of phi means that phi remains true for all the future conditions. Now the fourth one is U. meaning until. So phi 1 u phi 2 or phi 1 or phi u psi means like phi 1 must remain true until the phi 2 becomes true, and we represent it like this. So, like these are main four operators which form the basis for most of the temporal logic specification, which we will see in the next slides. For examples, these are similar examples which we have discussed in the previous slide. So let us move on to the temporal logic family. So we do have LTL, MTL, MITL, STL. These are all temporal logics. So over the time, these all have been developed to address different requirements. So first one is LTL, which is linear temporal logic. So it focuses on the ordering of the events, and and it's basically about the discrete time, like for different states it works out. The next one is MTL, which is metric temporal logic. It is kind of an extended version of LTL because LTL cannot specify the timing constraints. For example, you can see here there is no timestamp, right? But in the second example, we can see there is timestamp 222. So this is basically for including the timing constraints. The third one is MITL, which is metric interval temporal logic. It restricts, it's also a version of MTL, but it's a restricted version of MTL in a way that improved disability and improved the verification efficiency. We'll discuss more in about them in the next slides. So, and after that, there is STL, which is Signal Temporal Logic. It extends these all ideas further to the continuous valued signals. And this progression reflects a shift from reasoning about the Boolean events towards the reasoning about the real world sensor data. So let's start with the LTL. So, linear temporal logic, it's like one of the most widely used temporal logics. And we use the similar notations X, U in all these logics. So, LTL reasons about sequence of Boolean states along a single execution path. Its syntax is constructed using the logical operators together with the temporal ones like X, U, etc. For and here P is the atomic proposition. Atomic proposition is like some conditions, like phi is greater than some theta. Theta may be some threshold, like 30, 40, maybe a number. So then this becomes a preposition. Like it may have either true or false as an output. So for example, like G not of crash. So these are very simple examples for understanding the logic. So it states that the crash never occurs. So and similar GF, which we discussed, are used in it. So it's widely used in the software verification, model checking, protocol verification, and the hardware design. However, the LTL cannot express the quantitative timing requirements, as already told you. So it can specify that something eventually happens, but not when. So let's move to the next, which is MTL or MITL. So to overcome the timing limitations of LTL, Metric Temporal Logic introduced the explicit timing intervals. For example, like MTL allows the punctual constraints also, like F2 to P. So P happens exactly at time 2, So it may be like f0 comma 5. So it will happen between 0 to 5. But because it's 2 2, so it means like it will happen exactly at 2. But the reason we come up with the MITL is that such constraints often make verification significantly more difficult, because if we see the real world scenario, it may not be the exact timestamp, right? So there MITL comes Metric Interval Temporal Logic, which addresses this issue by restricting specification to non-singular time intervals. For example, like A provides f of b for timestamp of 0 to 1. So there is no exact time. It may be between 0 to 1 seconds. So exact timing constraints are not there in MITL. So as a result, MITL provides a practical balance, though it's a subset of MTL itself. Then signal temporal logic. So as far we saw like temporal logics primarily reason about the Boolean prepositions. And for example, statements such as like temperature high, it can be true, it can be false, right? However, the real world systems rarely operate on the Boolean signals. Instead, they generate like continuous valued measurements such as temperature of T, pressure of T, power of T, signal, right? Which continues over the time. So STL, Signal Temporal Logic, was introduced to reason directly over these continuous valued signals. So an STL formula is also built from the predicates defined on the signal. For example, we can take example like G, temperature of T is less than 100, or pressure of T is greater than 50. So these are some predicates, and G is like for converting into the formula. So these predicates are then combined with the temporal operators such as G, F, and U. So, as a result, STL is particularly useful for cyber physical systems, healthcare monitoring, industrial automation, and the anomaly detection too. So, unlike LTL and MITL, STL allows us to reason directly about the physical measurements. Now, at this point, it is very useful to understand like how temporal logic evolved. As we discussed, so we understood like LTL introduced the temporal ordering. It answered the questions such as like, will something eventually happen? Or like, will something always remain true? But MTL, on the other hand, extended the LTL by adding the timing constraints. Now, MITL is a refined version of MTL to make verification more tractable, easier. However, all of these logics primarily reason about the discrete prepositions, right? But STL represents a next major step because it reasons directly about the continuous signals. Now, in addition, STL introduces the robustness also, robustness semantics, or it generates a robustness score, which provides a quantitative notion of satisfaction. And this makes STL very useful for modern AI systems because rather than simply determining whether a system or a property holds, STL can measure like how strongly it will hold. We'll discuss like how we calculate that too in the next slides. So let us summarize the evolution we have discussed so far. So LTL provides temporal ordering, we saw, but does not support quantitative timing. MTL provides explicit timing intervals. MITL restricts MTL to improve the verification tractability. And the symbols are almost similar. The time domains differ, like it works on discrete time, it works on discrete or continuous both, because it may be step or it may be a interval of time for MTL or MITL. STL works on the continuous time period. And there are different typical use cases for these, which are like hardware verification for LTL, real-time systems for MTL, hybrid systems for MITL, and control, robotics, anomaly detection for STL. So, in many ways, STL can be viewed as the most practical temporal logics for the modern cyber physical systems because it combines the temporal reasoning, metric timing, continuous signal support, quantitative robustness, etc. So these combinations explain why STL has become increasingly popular in monitoring and AI applications. Now, robust STL semantics. So we'll see how it works. So we'll go beyond true or false. So traditional temporal logics provides the Boolean answers. A specification is either satisfied or violated. However, the binary view, as we discussed, can be limiting, right? Consider a specification like, for example, G, where temperature is less than 100. Now consider two signals. A signal A remains at 95 degree. A signal B remains at 10 degree. Now both specifications are like satisfying the property that temperature should be less than 100, but intuitively signal B is much safer, right? So Boolean semantics cannot distinguish between them because it's just true or false. So this motivates us for the robust semantics. So instead of like returning that true or false, STL returns a real valued robustness score, which we denote as rho, rho phi xt. So this indicates whether there is a satisfaction or not, and by how much it is. So the magnitude indicates the distance from the boundary. So, this additional information is one of the key innovations of the STL. So, let us examine the robustness more closely, how it works. So, suppose our specification is temperature is less than 100, as we saw. So, robustness will be like 100 minus temperature, means like threshold minus the predicates or the variable, which will be the row. It's one of the easiest example. So now we consider different temperatures, like for temperature equal to 90, robustness will be plus 10. For 95, it will be plus 5. For 100, robustness equals 0, like it's borderline. Now, if temperature equals 105, it becomes minus 5, like 100 minus 105. And for 120, it becomes minus 20. So the positive robustness here indicates the satisfaction. The negative robustness shows that there is a violation. And the farther we move from the zero, it either shows a stronger satisfaction or a stronger violation. And we have plotted this robustness to show how it works. So the green region shows the safe region, the red is the violation region because it's violating the rule. Now, this quantitative interpretation makes STL really useful for optimization, monitoring, etc. Now, the natural question is that how do we compute this robustness for the complex STL formulas? Because we see the simple formulas, right? So the key idea is that logical operators become the optimization operator. Like for simple atomic predicates, we saw like it's very simple, like xt minus c, it becomes the rho. Now here c is the basically our threshold, xt is the signal. Now for negation property, we see is as the negation of the rho will be the rho. And for conjunction, which is and, we take it as the minimization because both conditions must hold. And for that reason, we take the minimum out of them. Now for disjunction, it's or like rho of phi 1 or phi 2. It equals to the maximum of the both, like phi 1 or phi 2 or rho or psi, right? So because only one condition must hold in the OR gate, so it works like as the maximum out of the two. Now temporal operators handle in the similar fashion. So we saw for eventually here like rho of f1, it will be the maximum because the event can occur eventually at any time stem. So we take the upper bound for the robustness. Now, for the globally, in the similar fashion, we take the minimum robustness over the interval because it's kind of a condition which will hold for throughout the signal over the time period. So it's the minimum. For until it's a combination of like both because phi 1 must hold until phi 2 holds. So what we do is that we take the minimum of the row of phi 2. Phi 2 should hold at some time. So we take minimum here and then minimum of phi row of phi 1, which is phi 1 should occur, but we will take the minimum at which it occurs. And finally, we take the maximum because we want eventually it's gonna occur and phi 1 must hold. So it's a combination of maximum. First, we take maximum and then we take the minimum. So this is how it works out for the all the logical operators. So this interpretation transform the temporal logic monitoring into a optimization problem over the signal trajectory because we are optimizing either by taking minimum or maximum, as you can see in the charts as well. Now, most important application of STL is runtime verification. So instead of verifying a system before the deployment, runtime verification continuously monitors a system while it is operating. So workflow is like very straightforward. So sensors, our measurements are collected, and then STL monitor evaluates the specifications. Then a robustness score is computed as we saw, and based on that score, the system generates either the warning, alerts, or any corrective steps. So, for example, we can take example of water treatment plant. I'm again and again taking this example because this is one of the famous data sets, which is SWAT, Server Water Machine Treatment Plant, in which they do have these flow sensors, tanks, and there are a lot of data which they have collected related to the time series data. So we may specify like whenever a pump turns on, the flow must increase within the 5 seconds. So this is the formula for that. So I think we discussed in previous slides also. So the STL, what it does, it monitors, it evaluates this property continuously. There may be a set of properties, not only this is just one example. So if the robustness becomes negative, a violation is detected immediately, and this enables the real-time assurance of the system behavior. So, if it is positive, it remains in the safe zone. As it becomes a negative, there is a violation detected and it generates an alert. So, this is the idea about it. Now, the applications and the emerging directions. So, STL has found like application across many domains. In healthcare, STL can monitor the physiological signals such as ECG or heart rate streams. In autonomous vehicles, STL can verify safety constraints related to like distance, speed, or collision avoidance or something similar. In the industrial settings, STL is widely used for the fault detection, anomaly detection, or the predictive maintenance too. Now, in the robotics, like STL can provide the task specification safety guarantees. Now, most recently, STL has become increasingly relevant to the AI research. Like current research directions include like learning STL specification from the data, LLM assisted specification generation, some neuro-symbolic AI where we are having the neural logic and along with that symbolic logic of the STL or maybe other logic roots. Safe reinforcement learning, runtime monitoring of the foundation models. These directions demonstrate like how temporal logic is increasing. Now we'll go to the next part, like final key takeaways. So to conclude, let us summarize the main message from this talk. So first, the formal verification, which provides the mathematical guarantees that go beyond the traditional testing. Now, the second is temporal logic. So, temporal logic provides a language for specifying how system behaves over the time and how it evolves too. The third is signal temporal logics or temporal logic. So LTL, MTL, MITL, STL, they all represent a progression towards increasingly expressive temporal reasoning. And STL extends the temporal logic to the continuous valued signals and making it like more relevant to the real world scenario or the cyber physical systems. Now, fourth is the robust semantics, so which provide the quantitative information like how strongly a property is satisfied or violated. And finally, like STL is becoming the increasingly important or trustworthy in the AI field, like for runtime monitoring, anomaly detection, healthcare, autonomous systems. And the broader vision is that future AI systems will combine the data-driven learning with the formal specifications, enabling both like high performance and the mathematical assurance. So that's all for today. These are some references for review. If you want to go in depth, thank you so much for your attention. If you have any queries, please let me know.
Does anybody have a question? Yeah, I don't think. It was an awesome presentation, Aditi. Thank you so much.
Thank you so much for listening and your attention.